All right, well, it's wonderful to be here. I'm going to talk today about some of our work in deep equilibrium models. And this is really actually going to be based upon, so this is joint work with several, two of my students, Xiaoxi Bai and Ezra Winston, as well as a lot of collaboration with Ladlin Colton at Intel. This talk is really going to be based on 3 papers. 2 of the papers on deep equilibrium models. Oops, let me get the cursor back. 2 papers based upon deep equilibrium models, the one that appeared last year at NeurIPS, and one on multi-scale deep equilibrium models, which is about to be put on archive. Unfortunately, there's going to be 2 papers in this talk that are still going up on archive this week, but you can use it, I guess, as an ad for checking those papers out when they're released. The other paper this relates to is work on monotone operators and deep equilibrium models, which is also going to be out this week on archive. And I'm happy to, I'll provide some links at the end where this will be up this week. So this talk is first going to sort of talk about all 3 of these papers, actually. First, we're going to talk a little bit about deep equilibrium models as a whole, then about multi-scale DEQs, and then about these monotone operator DEQs. But to give a broad overview, what I'm talking about today kind of relates to the story we all tell about deep learning. So what we say about deep learning, at least what I say about deep learning often when I'm teaching it for the first time, is that deep networks, in some sense, kind of process inputs in a hierarchical fashion, right? So there's this classical example of, you have a deep network that in the first layer you extract edges, and the next layer you extract things like eyes and stuff like that, and then parts of faces, and you find full faces in the last layer. And what this talk is about is that, to a certain extent, I think this view is actually kind of incorrect. I think there's obviously some things that they're true about it, but it doesn't really capture the full story about what depth is really doing in deep networks. And I think we can gain a lot by rethinking depth. And so what this talk is about, it's going to be about how we replace deep networks with a single implicit layer network. And this is not, the old theory about, a single layer is good, it's exponentially sized. Now I'm talking about the same number of parameters. And things work just as well. And this is both in theory and in practice. This is a model called the deep equilibrium model. It does have some drawbacks, though, as it was first proposed last year at NeurIPS. And so I'm also going to talk in this talk about 2 follow-on pieces of work we've done to scale these to large-scale vision, modern computer vision tasks, and to sort of understand the theory of these things a lot better. And I'm going to touch on all 3 of these points. Okay, so to start off with, I want to talk about deep equilibrium models. As I mentioned, this is based upon our paper last year at NeurIPS. So to start off with, I'm going to start as our starting point as a traditional deep network, which looks something like this, right? Of course, they can be much more complex. They can have residual layers, things like that, but just take this as a starting point. We have these the hidden units of our network, which I'm calling the Z here, are typically given as some function of the previous layer. And so typically this is something like a linear operator W applied to these hidden units plus a bias term, and then you apply a nonlinearity like a ReLU or something like this. Of course, that linear operator doesn't have to just be a matrix multiply, it can be a convolution, many other things. But this basic form is kind of the building block for modern deep networks. And what I'm going to move towards is actually, sort of the first step of what we're going to get towards is we're going to consider a little bit of a modification of this network here. And we're going to modify it in 2 ways. The first thing we're going to do is we're going to add weight tying to this network. So I'm going to take this network that we have here, and I'm going to apply the same weight matrix W to all the layers. And that might seem like a big restriction. It's actually not. It's actually, I'll mention some theory in a second, but it turns out you can actually prove that any network you can construct with a normal kind of feed-forward network you can construct with these weight-tied networks. And more importantly, it actually works almost as well in practice. So a lot of modern networks actually are moving towards weight-tied structure because it isn't actually that big of a deal to do this. You just have a little bit bigger hidden unit, you weight-tie networks, weight-tie all the layers, and things work fine. So that's the first thing. We weight-tie the layers together. The second thing is that we add this input injection. So to every layer, we add some input, U, some matrix or convolution or operator, times the input X, and add that to the thing. Again, that's not too big a restriction. That's just saying that we keep around a little bit of the input and we add it to every layer. So the basic idea here is that these networks, despite what seems to be kind of their seeming limitations here, are actually very powerful. So They really aren't a limitation in practice. They really have, this is actually, if you squint at this, this is, of course, very related to a recurrent network. And things like this go back to the roots of things like recurrent backpropagation, which has been built a lot upon in previous years. It also relates very heavily, I should add, to neural ODEs. This sort of structure of repeatedly applying an operator and a nonlinearity is very, very similar to what neural ODEs sort of look like in practice. And there's also a lot of modern sort of practical networks that recovered this structure anyway. So things like trellis networks, which was an architecture that we worked on previously, or universal transformers. They've all actually sort of come to the same conclusion that you don't really need to have different weights or different layers. Things kind of works fine. So now we're at kind of an interesting point here, because now we're defining a network as the repeated application of this same function again and again, right? So we can think of a deep network as just the repeated application of some function. So zi plus 1 equals nonlinearity times wzi plus ux plus b. So this is our function here. But this is now sort of just the repeated iteration of a nonlinear function. And when you do this in practice, at least with networks that actually work in practice, what you will find is that if you repeat this iteration, then the networks will actually converge. The hidden units will converge to a fixed point or an equilibrium point. And that kind of corresponds to an infinite depth network. It basically corresponds to a point which I'm going to call Z star here, where when I apply this function again, things don't change, right? Things actually stay the same. And then, as I said, this sort of corresponds to the infinite depth limit of this network. And while there's definitely no guarantee this is going to happen for sure, the network could, of course, be unstable, or it could diverge, or it could oscillate. For a lot of networks in practice, this does happen. And if this does happen, this says, I think, something very fundamental about the nature of what these networks are doing. What these networks are doing, what depth is doing in these networks in some sense, is that it's computing the equilibrium point, the fixed point of some nonlinear dynamical system. And the idea of this deep equilibrium model, or DEQ model, that, as we presented it last year at NeurIPS, is that we just want to directly find this equilibrium point via root finding. So if we're looking for this equilibrium point anyway, if this is the product of deep networks, let's just go ahead and find this anyway, rather than iterating the forward model. And of course, I'm showing it in a very simple case here, where it's just literally a single layer. In practice, at least for the first part of this, I'll actually think about a little bit more complex things. So this simple function is like a single residual block or a slightly more complex cell, but it's just the repeated application of these nonlinear blocks. Now, of course, the question is, when you have a network like this, how do you train these networks? So this is non-trivial, but actually, fortunately, this is sort of the one workshop where I don't have to get into too much detail about how you train them. I think a lot of this has been covered already. And so what you do is that in the forward pass, you just compute the equilibrium point. So essentially, you use any method, like Broyden's method, to solve for this equilibrium point Z star. I guess I should have mentioned Broyden's is sort of a generic nonlinear root finding technique that is actually very similar to methods like LBFGS for optimization. So you find this equilibrium point, and I'm actually going to abbreviate this function here, the sigma, WX, et cetera, just as F of X star and F of X star and X, or Z star and X. So you have your equilibrium point, then you would do something like, often your actual output is not the same size as your hidden layer. So you maybe have one more linear layer, compute a loss to this. And that's the entirety of the forward pass. Now, I'll get to it in a second. The next step, of course, is how do you train these things? And the backward pass here is a little bit trickier. But fortunately, we actually know how to do this by all the sort of the work we've been doing in this field of implicit models and declarative networks recently. It turns out that even though these networks involve a fixed point computation in their forward pass, you can actually differentiate through it analytically using the implicit function theorem. This is the actual form it is. The precise form itself isn't too important. You have this weird sort of I minus a Jacobian inverse term. You wouldn't actually compute that Jacobian and invert it. That'd be too big. What you instead do is you solve for these inverses using some indirect method, like conjugate gradient or something like that. We actually use Broyden's method for that as well. Now, one point I want to make sort of that I do want to highlight here, though, is that everything we're talking about here is using this analytical form of backprop. So I am not saying we should unroll our forward computation to do this. That would require that we keep around all the intermediate iterates. And one of the big benefits of these implicit models is that we only need to keep in memory this one equilibrium point. We actually don't need to keep around the intermediate computation like we would if we actually unrolled the computation. So it's important that I'm advocating here for analytical computation of the equilibrium point and analytical backprop through it. Now, also these things have some nice theoretical results. So it turns out that as I mentioned, a single layer DEQ is actually sufficient to represent any feed-forward deep network, including deep networks with residual connections and stuff like that. It's a simple proof. It's not actually what you do, and basically you just stack all the layers of the network together and keep applying a function like this. It's important to know this is actually just for the theory. It's not what's done in practice. So in practice, you just pick a little bit larger hidden unit and you solve these things, and that works just as well as other networks in practice, as we'll see in a second. And the second theorem, that sort of theory we have about this, is that a single layer DEQ is sufficient also for representing anything like a multi-layer DEQ. So there's, despite the cool sounding name, it would not actually be useful to stack multiple DEQs together. So a stacked DEQ is not very useful because you actually can always compress multiple equilibrium solves into a single equilibrium solve. Now, this does leave open some interesting points, though, like that you sort of might naturally think about this. So, what about like uniqueness of the fixed point? What about stability of these solves? Everything's very unclear now, and actually a large part of this that I'll get to in this talk is sort of trying to address those things. So, how well does this actually work? Well, it turns out that on a lot of tasks, this works sort of incredibly well, these sorts of models. So we use this to we applied this to a sequence modeling task on the Wikitext 103 data set. And this is typically measured by perplexity, how good a language model is. And compared to sort of state-of-the-art language models, like a Transformer XL language model, at the same number of parameters, these DEQ models with basically the equivalent number of parameters with a similar sort of functional cell end up outperforming the explicit depth model. So for example, with 5 million parameters, we get a lower perplexity and a lot lower memory consumption because we, again, are not having to store around intermediate layers together. Similarly, for a network like a trellis net, we can improve upon perplexity and vastly here upon memory consumption. And this sort of pattern continues. Now, I should mention that we're still not quite up to the largest size training yet, just because we don't have the biggest transformers are trained on things like TPUs. We haven't done that yet. But these trends seem to continue. For mashing parameter count, you get better performance. There are some drawbacks, though. So first of all, DEQs right now are slower than traditional networks because finding that fixed point tends to be slower than a typical deep model with an equivalent number of parameters. And we also need to get actually pretty reasonable conversion to the equilibrium point. You can't just run like 5 iterations of Broydens. You have to get a little bit more accurate for the implicit function theorem to really apply. Then maybe more fundamentally, single layer DEQs, as we present them here, it's sort of great theoretically, but they lose a lot of the multi-scale nature that we do believe is sort of inherent to computer vision and tasks like this, right? We do believe that processing an image happen at multiple scales, and we don't want to give that all up just for a single kind of fixed size layer, period. The other thing is that, as I mentioned before, questions like the existence or uniqueness of the fixed points is largely heuristic, and it requires a lot of tweaking to get right in practice. So actually, there was some reasonable recent papers that sort of said that they tried DEQs and basically said that, oh, it didn't work in our setting because it wouldn't converge or things like that. So in the next 2 parts, I wanted to sort of very briefly highlight some of the current work we're doing to address these deficiencies. The first work I want to talk about is this notion of multi-scale DEQs, which I highlighted earlier, and as I mentioned before, is going to be posted to archive this week. So the challenge of applying DEQs to vision domains, there's actually a lot of challenges, right? Images are inherently hierarchical in some sense. We really do want a way of analyzing them at different spatial scales. And they're also large, and so which presents a few problems for DEQ models, right? So if you think about like full HD video images, if you apply a convolution to these things as your linear operator, you would need to apply a whole lot of convolution before that kind of effect mixed over the whole image. And it turns out even though our methods are more efficient, you still can't even store all the intermediate Jacobians and things like this for Broyden's method with images and inputs this big. And so to do this, to sort of handle these situations, we developed a slightly different DEQ model, which we call the multi-scale deep equilibrium model. And the key idea here is that we're going to do the same thing, but as a normal DEQ, but our hidden unit here, the Z, the Z star, the equilibrium point, is actually going to represent multiple different spatial scales simultaneously, and we're going to solve for the equilibrium point for all of them at the same time. So I'm going to sort of build up what this looks like. So we have our image, say a panda image here. We're going to represent a hidden unit that captures the image at multiple scales at the same time. So we have, a high resolution scale Z1 and a very low resolution scale Zn, typically with more channels though, like in normal deep networks. And what our function is going to do, what our F function, right, the sort of the single unit we're going to apply here, what it will do is it will apply a residual block to all of these scales simultaneously. It'll also add input injection to the highest resolution scale. Then, importantly, it will mix all of these together. Okay, so it'll, by downsampling or upsampling, it'll mix all the spatial scales together. And this whole block now is actually what we call our function. That is our function that we apply to the image. And then we use a multi-scale equilibrium solver to find simultaneously a set of equilibrium points that is satisfied over all these scales at the same time. Sort of is a fixed point of this F, this multi-scale F. And then we can send these things, high resolution versions or low resolution versions to a loss function. One of the very nice things about this architecture is that you can think of these multiple different resolutions as kind of different heads for different tasks. So there are, high resolution losses like segmentation losses or low resolution losses like classification losses. You can actually apply all of these to the same model. And what we'll actually show in a few slides is that you can apply the same MDEQ model, multi-scale DEQ model, to both classification or segmentation tasks and perform very competitively with the current state of the art. We also had to fix things a little bit to make them more memory efficient. So we implemented a limited memory Broyden solver, similar to like an LBFGS type method, to further reduce memory requirements of finding the fixed point. But this is basically all that we had to do to make this thing work. Now, how does it work? Well, I'll actually go through the results very quickly here because it works well, but that's not sort of the point I want to highlight. So something for domains like CFAR10, these are actually been the sort of the largest domains that previous implicit models like neural ODEs or other similar models really apply to. Or this is sort of amongst the largest scale that they apply to, of course, for vision tasks. And here, if you compare sort of how a pure neural ODE or a pure augmented neural ODE does against our model, what you find is that our models sort of for when you fix the number of parameters, again, the MDEQ here, which is the last column on the right here, sort of vastly outperforms these other implicit models here, even outperforms like a ResNet of a similar size. This is actually also with no data augmentation to replicate some of the results that were used for these papers. And there's also a big advantage of using this sort of multi-scale treatment. So if you use a single DEQ, like a single convolution, you just sort of keep it the same size the whole time. We call this a single stream DEQ, and it performs much worse on these domains. Similarly, if you of course, these are not groundbreaking results for CFAR by any means. This is very small scale models. If you increase parameter size, of course, our methods scale up, and you can get things that are on par with sort of good methods for CFAR. Though even this is sort of a quick experiment here and not really our focus. If you look at the story for ImageNet, the story kind of is similar here. We're going to compare sort of small scale models and larger scale models. And the point I want to make is actually that I'm just taking a bunch of kind of traditional models for ImageNet. And what we find is that with small models, we're definitely not the best model per parameter count, but we're sort of right up there with the state of the art in terms of top one accuracy, beating things like ResNet 50, beating things like ResNet 18 certainly with similar scales of parameter counts. And then if you increase size even further with like ResNet 101s or DenseNet models, you similarly get very good top one performance. And again, this is far, far beyond what, as far as we know, anything is sort of being done with implicit layer models for these sorts of large scale image tasks. The last thing I want to highlight is similar results on segmentation. So we're talking about here the cityscapes image segmentation, visual semantic segmentation task here. And again, maybe going through this briefly because I don't want to have it spend too much time. For small models, MDEC here, which is on the right, gets very competitive MOU, and as you scale things up, it actually beats models like DeepLab v3 or PSPNet. Again, not quite the current state of the art, but almost second to the current state of the art in terms of this performance. What's very impressive though, and that point I actually want to highlight here. Here are some. Here, of course, we're required by law to include some screenshots of the actual segmentations it produces. They look pretty good. I guess that's all you should get out of that figure there. The point I want to highlight, though, that I think is really cool here, is that it's the exact same model that we apply to ImageNet as we apply to semantic segmentation. The only difference is that on ImageNet, you apply classification loss to the highest resolution, and on Cityscapes, you apply a segmentation loss on the highest resolution. And this is the only difference. Other than that, these models are identical. You actually pre-train the model with ImageNet before you apply Cityscapes. That's very standard. But there's no backbone. There's nothing like this when it relates to sort of traditional segmentation. And it really does show that these things are they are not just problems. They're not just for toy problems. They really do scale and are competitive with state-of-the-art on large-scale vision tasks. So finally, though, I want to highlight some additional recent work we're doing, which again will be on arXiv this week, on sort of understanding better the theory of these networks. Because the reality is, so far, there's very little we can say about this fixed point. Even for a single iteration like this, where this is a single layer, it can be very difficult. This still is a nonlinear dynamical system. And in general, it can be very difficult to establish existence, uniqueness, stability of these fixed point iterations. And so, unlike neural ODEs, where things like Picard's theorem actually can guarantee existence and uniqueness, DEQs do not have, or traditional DEQs do not have this property. The other thing is that, I'm talking about sort of one layer being all you need, but the one layer of an MDEC was really pretty complex, right? It was sort of included residual blocks and upsampling, downsampling, et cetera. So we really do want to think about analyzing a simpler formulation that is still representationally powerful. And to do this, the tool we're going to bring to bear here is a monotone operator theory. So this is a beautiful theory that sort of actually relates to how how a lot of convex optimization methods are solved. So things like proximal gradient methods or ADMM. A lot of these things are based upon monotone operators. And there has been a little bit of work actually by some of the authors of monotone operators looking at connections between these things and deep learning, though not going sort of in the same direction that we're going. And so here's the key result that I want to which I'm not going to prove at all because it actually is a little bit, but think of it kind of like an ad for the upcoming paper. The key result we have is that if you consider a single layer DEQ, like this. So Z star equals some nonlinearity applied to a linear operator applied to Z star plus a linear operator applied to the input plus a bias term. Then there exists a unique, so there is guaranteed to exist a unique fixed point of the system, provided that the weight matrix obeys some positive definiteness condition. And basically, the 2 times identity has to be greater than in a positive definite sense of W plus W transpose. That's condition number 1. Condition number 2 is that the nonlinearity itself, so this nonlinearity here is given by a prox operator, a proximal operator for some convex function. Proximal operators are minimize the square difference of a function or of a point with some input plus a convex function. I won't get into what that is. Again, if you're unfamiliar with those, the paper will describe all these things. And this result actually comes from the fact that a fixed point can be viewed as a solution to what's called a monotone operator splitting problem. So there's actually a very deep connection between the fixed point that DEQs are trying to compute and monotone operator splitting. And it's really sort of a beautiful theory, and it's sort of laid out much more in the paper we have coming up. Now, one thing that's important to note is that we actually are not requiring that W kind of be stable in the normal sense. It can still actually have very large operator norm. It just needs to be large kind of in the negative or imaginary components. So actually can have operator norm, which makes even the fixed point iteration, so you just repeat this thing, actually can be unstable. But by monotone operator theory, you actually can still prove that it will have a unique fixed point, even if the iteration is unstable. And of course, also monotone operator methods give you ways of finding that fixed point that are more efficient. So this is sort of, these are these two conditions we have to connect monotone operators and DEQ models. And the question is, are these reasonable assumptions, right? So can we reasonably assume that the nonlinearity is a prox operator and that we have this positive definiteness condition? And for the prox operator, yes, a lot of sort of natural nonlinears we use anyway, like the ReLU, are already prox operators, and a lot of them that aren't quite can be represented arbitrarily well with prox operators. Now, secondly, though, is it reasonable to assume that we have this sort of condition on the weights, that we have this weight condition that the W matrix satisfies a certain linear matrix inequality? And there's the answer sort of is no. This actually does happen to be true at initialization for a lot of initializations of these sort of common initializations, I should say. But during training, this will be violated almost certainly if you train a network normally. And so the trick that we use here to actually make this all work is that we have to reparameterize the network, or parameterize the network in a way that enforces this condition. So if in particular, if you define W in this manner here for other operators, other linear operators F and G, and this sort of involves a negative definite component and kind of an anti-symmetric component here, then you actually can guarantee this will be the case. M here is just actually a small constant, a small positive constant. And so this is really the key here, is that we're defining a network such that monotonicity, which is what this condition actually enforces, is always satisfied by the network. Now, the advantages of this parameterization and this formalism is that, as I already mentioned, we have a unique fixed point. And we can also use operator splitting approaches, not just sort of to guarantee there is a solution, but we can also use them to find these solutions much more efficiently than we would otherwise. So methods like Piesman-Rackford iteration, which was actually very related to also Douglas-Rackford iteration, which you may have heard of if you've looked at things like ADMM and all. These are methods that converge much more rapidly than just the typical sort of iteration of our function we would normally think about applying to find a root. And this is actually a very powerful theory that gives us guaranteed ways to get linear convergence of our equilibrium point. The other very cool thing is that the backwards pass can also be computed via the implicit function theorem and also has an operator splitting formulation, which lets us actually reuse these same efficient methods, not just for the forward pass, but also for the backward pass. So how well does this work? So in some initial studies here, this is not going to be the same scale as the MDEQ models, but it's actually sort of a similar kind of idea here. We can actually use a simple multi-scale network where we sort of have just the downsampling components of the network, not the upsampling ones of the full MDEQ. But here, basically, the matrices are either just square convolutions or they are downsampled convolutions. There are tricks you need to do here to enforce the positive definiteness of this matrix, and you have to be able to compute actually its inverse via an FFT to use the really fast operator splitting methods. But we do both of these things, and we do actually get results that are still quite competitive. So with a modest number of parameters, we're able to substantially still outperform the other methods that have guaranteed solutions. So this is now in the domain of these methods that sort of we know are always guaranteed to converge, that have a well-defined fixed point, and we're still getting most of the benefit from these DEQ models. Okay, so sort of to conclude this sort of whirlwind tour here of these three papers. The idea of deep equilibrium models is that one layer kind of in some sense is all you need. You don't need to have explicit, very deep networks. You actually can just use a single layer network as long as you allow for like an implicit type of layer instead of an explicit layer, explicit many layers. And not only that, these things are not just sort of nice theoretically, they also are very practical. They scale to sort of modern current vision tasks. And we are getting a much better handle on the theory of these things using the framework of monotone operators. So at a high level, I think this bodes well in some sense for the return of maybe shallow learning again, as long as you understand shallow learning to be shallow, implicit, very structured learning. And all these papers and code, including, of course, the MDEQ and the monotone operator papers, will be available within a few days at my website. I want to thank again Xiaoji and Ezra, who are the main students that did all this work. Thanks very much.